Now let's talk about scaling, right? So something you might not have pay attention. The whole history of semiconductor can be summarized as one word: scaling. When people have their first transistor, it's very big. If you look at the picture, how they got the first Nobel Prize, they invented the transistor in 1947, right? It's huge, bigger than your laptop. But nowadays, your laptop, just a single chip, contains more than 1 billion transistors. Just a single chip, okay? So that is why semiconductor is so important. And there are two major Nobel Prizes about semiconductor. One is the transistor, another is integrated circuit. They found that we actually can integrate a lot of devices on the same substrate. But we don't need to do it one by one. We do it all in a batch. What is integration? Imagine you have a city. In this city, how do you build a house? You build one by one, right? So if I want to build 10 houses, it takes me maybe 10 units of time. If I want to build 1 billion houses, it takes me 1 billion of time. This is not scalable. Integrated circuits is what? It's just like that you build a house by first. Let's say you have the technology. Put the concrete everywhere in the city. And then you somehow can etch away the connection between this concrete, okay, in one time. Well, maybe you have a mask shadowing, and then you shoot some bullets or dynamite to here, expose them, then you have all this house. So I can build all the cuboid at one time, right? And maybe then here you say, I also can then make the hole to all this house at one time. Let's say you can do that, right? Again, by using a mask, you shoot the bullets, but these bullets are blocked by this guy, cannot go through. This time, this can go through, right? This time you have a mask like this, right? You make a mask on the sky, and then you just shoot all the bullets or dynamite, explosive, whatever. Then you come up with this hole, okay? After that, you just have able to deposit a very large layer of roof one time. And then you do the mask again. Shoot the bullet so that you cut off this. Isn't that I created 10 billion boxes at the same time? This is a bad house, but it can live people. People can go in, right? This is called integration. And the whole history is that, how do I make this even smaller? Because I'm not building a house. I'm just building a functional unit. I keep squeezing them while they still function as what we want. Maybe you don't appreciate much. Let's do a quick math and then stop this class. If I have a 1 cm by 1 cm silicon substrate, okay? I start with transistor, which is 1 micron by 1 micron. How many transistors I can put? 1 cm means 10 to the power negative 2 meter, right? So the area is 10 to the power negative times 10 to the power negative 2 meters squared. 1 micrometer is what? 10 to the power minus 6 times 10 to the power minus 6. Yeah? So this gives me what? 10 to the power 8. I can put 100 million transistors in this 1 cm area. Okay? If I am able to shrink this one to 1 nanometer by 1 nanometer, then this becomes 10 to the power negative 2 times 10 to the power negative 2 divided by 10 to the negative 9, 10 to the power negative 9. Which means it is decreased by 1 million times. It becomes 10 to the power 8 times 1 million, which is 14. So by shrinking this device from 1 micron by 1 micron to 1 nanometer by 1 nanometer, using the same process, same amount of money, I can have 1 million more transistors. It means my chip can function 1 million times better. Right? Of course, this is a fake number, right? But I want you to see the idea because of the area. So this shows the year, right? The size of the transistor. It starts with 2 micron in 1980. It goes down exponentially. This is log scale, and reach 50 nanometer in 2010. And now we are talking about 10 nanometer. And this is called a part of so-called Moore's law. We'll talk about that later also. Okay, so the scaling is one thing, and the change evolved transistor is another. We start with bipolar transistor, but then later we go to MOSFET. Do you know why? You can pause it to think, but the main reason is because leakage. Bipolar transistor has the base leakage, but MOSFET gate leakage is almost zero. That's why we go to MOSFET. Later again, we found that single MOSFET is not enough because we start with PMOS, and then not good enough, then we use NMOS. But then later we go to CMOS. We use CMOS, we use NMOS and PMOS together. Again, why? Because of leakage. This time it's the circuit leakage. CMOS will consume no current ideally when it is in off state. Nowadays, we are going into another problem again. Do you know why? Again, it's leakage. Now the transistor is so small, even you turn it off, it's leaking current. The gate oxide are so thin, when you turn off, there is still current, there's tunneling. That's what we want to cover. So we come up with all this invention, silicon on insulator, FinFET, 3D transistor, whatever new architecture, we just want to deal with the leakage. The leakage is so high that if we don't deal with that, if we did not take all this that we did in the last decade, now for a CPU, if it's just in the sleep mode, not doing anything, it's hot enough to cook the egg. The leakage is more than 100 or even 1,000 watts. But good, because we have done a lot of engineering, now we can live with that. And that engineering comes from device all the way up to software power management. This is a code optimization, right? I'm not very clear about what I'm saying, but I keep dumping some keyword to you. When we go through this class, we will keep revisiting this keyword because everything we're trying to do is related to this keyword we're talking about. The size, the leakage, the control, the tunneling, whatever, the speed, right? This is something you need to put in your mind, okay? So let's stop here. Continue to talk about the scaling. Last time I just stopped there. So last time, I basically tell you that in the whole history of semiconductor, actually before that we did not mention, we start with vacuum tube. Vacuum tube is something that differentiates, if I'm correct, I heard about this story, differentiate Russia from US. At that time, it was Soviet Union. So both of them are very good in technology. Russia keep thinking that they can make the vacuum tube very, very small. And it is very difficult. If now you study the vacuum tube technology, all the equations are more complicated than the MOSFET equation, right? Russia keep doing that. They make it very, very, very small, very, very high tech. It's an art. But then US decided to go to semiconductor. And eventually you see the big difference. All the semiconductor industry came from US, right? In the 1980s, 1970s. Because vacuum tube consume too much power. So later we start to use so-called bipolar transistor. And then later it consumes too much power again. So we use MOSFET. And then MOSFET, if just NMOS, it also consumes too much power because you need to use the so-called pseudo NMOS architecture. You actually make an inverter like this. And this structure, when you put, for example, input equal to 0, right? Input equal to 1, output is not exactly 0. There's a current always flowing from VDD to bottom because the top is resistant. So gradually, when you put more transistor on the chip, you consume more power again. And eventually, you use CMOS, right? You have the PMOS and NMOS putting together. So that in steady state, you don't have any power consumption. But nowadays, when we are in 2000, we have the same problem again. Devices are not ideal. I'm going to explain today. Even they're both in off state, they are leaking. And now they will have current going through the gate called tunneling, quantum effect. And then we have PN junction leakage. So that's why we come up with a new transistor and new architecture. So the whole history of the semiconductor, you can say that is scaling, but another main point is about reducing the power consumption. If you can invent something, have very low power consumption, you will be the king in this area. Okay. But that's okay, right? Now our point is, how about let's just look at how they scale the transistor. They make it smaller, smaller, and smaller, right? This is usually what people do. They talk about Moore's law. The first thing we think about is we make the transistor smaller, right? But how can we make it smaller, right? You can make it smaller, but how can we make it smaller so it is still working, right? So let's just do a quick review on Poisson equation. As I said, I don't require any prerequisite, but here I assume you know some EM, right? If don't, doesn't matter. I will only emphasize the important point. And the important point and the points that I think are at least important to device physics, I want you to memorize, right? It sounds ridiculous. We keep saying that graduate students need to not just memorize the equation, right? Here, I'm not asking to memorize the equation. I want you to memorize the feature. Of course, in this process, you don't just memorize it. You do it through observation and to see, to appreciate the importance of different aspects of the equation, okay? If you say Poisson equation, I can write it very complicated. I can say this one. I can write something like this. This is a Poisson equation. This is 3D version, right? I even don't need you to understand this. This is Laplacian. Right? Let's just look into the 1D version. Do you know what is the 1D version of a Laplacian? Anyone? It is just the second derivative. D squared phi dx squared equal to negative rho divided by epsilon. Now, if you get confused by 3D, don't worry. I am not asking you to do this. But the reason I write out 3D is once you understand 1D, I hope that you can correlate to 3D. If someday some people give you a 3D equation, you won't just give up. You won't just say, I don't know that. He's the expert, she's the expert, I'm not. No, you know everything. You just think about what you learned in 1D. Because basically a Poisson equation, right, is telling you the relationship between the potential, the location, and the charge. Okay, can someone tell me what is phi here? What does it mean?
Electric potential.
Thank you. Potential. Electrostatic potential. Since we're doing EM, so it is just write potential. Okay, how about rho? What is this? Do you remember?
Charge density.
Thank you. Charge density, right? So we of course have to be careful what type of density we are talking about. In here, we in particular are talking about Coulomb per cm or per meter. Here I use per cm squared. How much charge in per cm cube? Okay. Now, what is epsilon? Now, if for some of you, you forgot about this, that is definitely fine, right? But why I want to ask students, because I want those to remember to refresh, and at the same time, you also can participate, right? So do not feel that how come other people know of this? If I don't work with this for 2 years, I will forget also. I can tell you, I'm looking at my cheat sheet, right? So no problem to forget. The reason, I mean, the point is we want to have an insight, right? Anyone remember what is epsilon?
Permittivity?
Thank you. Permittivity. This is something we're going to deal with a lot, especially for capacitor, right? It is, units is a little bit weird, right? Farad per cm. I even don't know if I do it right. So let me erase it, but I think it's Faraday per cm, right? You can check it later. Permittivity, why this is important. For example, for silicon dioxide, what is the permittivity? Is this 3.9, right? You don't need to memorize, but if you are in the semiconductor industry, you should know this is 3.9 times 8.854 times 10 to the power negative 14 Farad per cm, right? I think I'm right, the unit, but still put a question mark here. This one is the so-called epsilon zero. This is the vacuum permittivity. For different material, you have different effective permittivity, right? Just recall, what is capacitance? I don't know if you learn about this equation, but we need to learn it. You definitely need to memorize. Just tell me, if I have a larger permittivity, do I have a larger capacitance or smaller capacitance?
Larger.
Thank you. For vacuum, right, it is 1, right? 1 times this one. So this one usually call it relative permittivity, right? But anyway, I just put epsilon here. It's larger, so it goes to the denominator, the numerator. What if I have, for a capacitor, right? This is a capacitor, and this is epsilon. And it has a thickness, right? If I have a thicker capacitor, do I mean thicker dielectric, do I have a smaller or larger capacitor?
Larger.
Smaller.
Oh, smaller.
Smaller.
Right. I don't think you can always get it right, right? So thanks for answering, because I can get it wrong also. But I'm so familiar with this because my research is all about this. But why I want to ask this? Because by asking yourself, what is the relationship of a quantity to the basic quantity, you can write down the equation easily. It is epsilon divided by T. Is it exactly epsilon divided by T? Actually, as an engineering, especially when you have a computer, it really doesn't matter. The most important is you know that it's proportional to epsilon divided by T. That is good enough for you. No one is calling to test you, hey, is there a constant in front of it? But of course, the exact equation is this. And it also depends on the unit system we are using. If you go to physics, they say, are you using CGS or using SI unit? You will see completely different equation. The equation I'm writing here for Poisson equation is also in SI, right? If you try to Google for Maxwell equation, you see that CGS and SI units are completely different. The form, even the form is different. Not just, I mean, the form is the same, but you will see a lot of difference, right? It's not just a pure constant difference. Any questions so far? Although I say many things, right? But that is the idea. We're going to go through this whole semester. But we are not trying to go through equation by equation. We try to do this for different devices. We don't have the time to play with the equations, right? But this is two equations very important. It's okay if you forget Poisson equation, no problem, no need to memorize. If I want to test you, I'm going to give you the equation, okay? Now with Poisson equation, why it is so important? This is one, right? It is that, you know that if I put a PN junction together, for example, I have a N-type material. I have a P-type material. This is N, this is P. We will do more later. I think this is very confusing. But remember, when I do this -9, is the so-called Fermi level. This is the conduction band. This is the valence band. And this is the Fermi level, right? Now you may say, oh, how come I don't know this? How come I'm not very familiar? If that is the case, I do want you to review p-n junction theory a little bit, but no problem. We're going to keep reviewing. You will see that we keep doing this, and that's why you need to study p-n junction for your basic physics, because we keep using the same concept for all devices, right? But the point here is that now you know that if I have an N-type, it means I have a lot of electron here. So the Fermi level is close to the conduction band. If I P-type, I have a lot hole here. The device is very close to the valence band. Okay? Anyone have not heard about p-n junction here? Can you let me know or send me in a private chat? Remember, you here, I don't assume you know many things. It's okay not to know something. If you tell me that you don't know something, you are helping others. Remember this, we are working as a team, okay? Whatever you ask, you are helping others. Because for some students, they might think that they know, but when you ask the question, they realize that they cannot answer, okay? So if I put a p-n junction together, then if you remember, we will have something like this, and which is wrong, right? What I'm drawing. It has to be the other way. Why? When it is far away from the junction, right? This is N, this is P. So far away from the junction, of course, I still should have the valence, the Fermi level close to the conduction band. Far away from the junction at the P side, I should still have the Fermi level close to the valence band, correct? Now, what is the physics going on here? What happened to this region? Can someone tell me what happened to this region?
So the first,
charge.
Sorry.
so the band gap has been lowered because there is donors and acceptors, and since when you put them together, so there's gonna be this. What do you think of the Fermi level? And so since it's straight across, that you're saying there's no current going through the p-n junction.
Yes, there's no current going, yeah. But this is not what I'm trying to fish for. Sorry, my question is not clear. But,
is it the diffusion and recombination of the electrons and holes happening there?
Yes. So sorry, is my question not right? So, have you heard about depletion region? I think you heard about that, right? Depletion. Yeah. So I think you know that, but sorry, I was not asking the right question, right? So what I'm trying to say is in this region, it becomes depleted. What is depletion? Now, let's look at this one. Don't think about band structure. If I have a lot of electron on the left, a lot of hole on the right, and then I put them together, what happened to the electron? Electron wants to go to the right, and the hole wants to go to the left, correct? It's just a random motion. Probably if I say this oxygen and this hydrogen, if you put these two gas together, what happened? Oxygen go to the right, hydrogen go to the left, right? What makes them go to the right and to the left is the diffusion, like what you just said, right? So when you put the junction together, electron tries to diffuse to the right. Because I have a lot of electron, the electron move not because of electric field. It moves because of diffusion. So two very important processes in semiconductor. Electron diffusion. Hole diffusion. This is one process, diffusion. What makes the electron or hole move is diffusion. So if the electron diffuse away, what happens? I say, I lose electron. I am depleter of electron. That's why it's a depletion region. Okay. Similarly, the hole goes from right to left. The hole, this region, this one, lose the hole. And then you say, I'm depleter of the hole. Then it is a depletion region. Is that clear? Any questions? But now go to, so that's what you have been telling me, right? You're just saying that, oh, no current because electron go to the right. Now, can you tell me again? I just say that the electron keep going to the right. Why do you say that there's no current? You just mentioned, but can you repeat? Electron go to the right. Will it keep diffusing forever? Then I have electron just keep going, and then the whole n region depleted of electron. Will it do that forever?
No.
No, why?
Because the holes are going the other direction, so they're recombining. So the electrons are combining with the holes, so there's going to be an electric field that's going to build up in the depletion layer, and current can't go past unless there's a voltage that you apply.
Excellent. There is one glitch let's discuss in the future. You say about recombination. That is not necessary, but you mentioned the main point. When the electron goes to the right, then what will happen? This part becomes more negative, and this part becomes more positive, right? Because electron go to the right. Same for the hole go to the left. This part becomes more positive. This part becomes more negative. So you have an electric field. Electric field is pointing from here to here, right? This is the electric field. So as a result, electron will go back. Electron drift. And the hole will also go back, drift. And they will balance. So theoretically, I keep diffusing electron to the right, but then it just being pushed back by the drift current. Okay, imagine you have a border, right? A country A and country B. Let's say country A has a lot of population. Country B have very few population. Country A people will just diffuse, right? Randomly, they will move to the country B. But eventually, maybe country B doesn't have enough resources. They set up the rule. Wow, no more immigration. They just deport you. Right? Or maybe this is a very bad analogy. But basically, what I'm trying to say that is, then you achieve a balance. Or not deport. Maybe the better way is saying that country B now becomes too crowded. Then economy become worse. Then they don't want to go to country B anymore. And then you have a force to drive you back to country A because there are more job opportunity, right? So eventually, diffusion and drift achieve a balance. Is that okay? So that is the depletion region, right? So why I say so much? Because I want to introduce the last thing before we go to scaling. And what I'm going to say now is this. What is the width of the depletion layer? Right? How do you find the width of the depletion layer? Well, go back to your textbook and find it. What we do is to solve the Poisson equation. Right? I'm not going to show here. because this is not the goal of this class at this moment. Later, when we go to MOSFET, if necessary, we will do that, but I'm not going to do it here. But however, it doesn't stop you from thinking, right? I can tell you the depletion width, W, is proportional to a few things. I don't know if you still remember. Do you remember what is its relationship to the doping concentration? If I have a very heavily doped region, is the depletion width to be shorter or wider?
Shorter.
Thank you. If you forget, no problem, because I forget also, right? The reason I'm trying to go through the exercise as the capacitor. So I put in the denominator, right? Do you still remember if I apply a very high bias, reverse bias to the junction, would the depletion width increase or decrease?
Increase.
Increase.
If it's negative, it increases. If it's positive, it decreases.
Very good, right. Now, so what Alyssa now saying is kind of, I don't know, right? I don't know how good she is in the device physics. It can be like her memory is so good, she memorized the equation. Or she already have an insight in her brain. She already can imagine that if I apply a bias, for me, it's like this, negative, I apply a positive bias, this one is going to go down, this one is to go up, then the depletion is going to get wider and wider. So this is another insight, right? So I guess she probably have the insight. She probably cannot remember the equation. No one can memorize that, right? So if we apply negative bias, it will go. So this is like this. Maybe you cannot get it, but basically we have a built-in potential. And if you have a negative voltage, then this one becomes larger, right? So this one will be on the top. And maybe you probably don't know, what if I increase the permittivity? Is the depletion width going to increase or decrease? No one knows, right? But if you think from capacitor's point of view, you will see that it is increased because the depletion region itself is a capacitor. So capacitance proportional to epsilon. So if I increase epsilon, it means my capacitance will increase. And what is the meaning of capacitance? Is that for a certain bias, how much charge I can have, right? So if I have a larger capacitance, I only need a smaller depletion width, because in that case, I will have I can support that system, right? If you go through this, right? But you don't need to memorize it, right? But what is the full equation is this. And then you also need a square root. Now I go through this, I'm not asking you to memorize this equation, but then the point is that I want you to have a feeling. Why? Because when people say, no, I'm not going to use silicon, I want to use germanium. What will happen to the depletion width? You don't want to go back and check and then calculate. From this equation, you know that, oh, depletion width will be wider because germanium have larger dielectric constant, right? Why? Because you are going to use this to analyze an even more complex device system. So if you have this insight, it helps you a lot. So why here? Now, this one, just take it as given. No worry about derivation. If you have time, go back to see the derivation. If not, the key points are here. Poisson equation, even you don't know, you have to know that it is just like I don't know the law, no, I don't know the constitution of US, but I know it is here. If I need to do something, right, can I, for example, do robbery, right? Can I stop people from freedom of speech? If I don't know the law, I know that I need to check it. Same for Poisson equation. This is the law, right? Maybe you don't know exactly what it is, but you remember we have this. And if you can memorize this form, it is even better, right? So let's keep practicing this until the end of this semester, okay? So